Presentation of deep learning embedding technique for categorical feature encoding. We proposed a deep learned embedding technique for categorical features encoding on categorical datasets. Our technique is a distributed representation for categorical features where each category is mapped to a distinct vector, and the property of the vector are learned while training a neural network. We will start by presenting the content of our presentation. Task 1, we introduce the preprocessing of the data. Task 2, we present different machine learning models which we have built. Task 3, we present the different metrics which have been used to evaluate the model. Task 4, finally, we give the conclusion of our presentation. First of all, we are going to describe the datasets. In our study, we have used 3 categorical datasets: the bank marketing dataset, the adult income dataset, and in-vehicle coupon dataset. Preprocessing the data is a very important step because it helps us to clean the data, check if there are missing values, and get the data ready for the training in the neural network. The first dataset is the bank marketing dataset. The second dataset is the adult income dataset. And the third dataset is the in-vehicle coupon dataset. The first stage is very important because preprocessing the data is one of the major steps when we are dealing with any kind of text model. We first start by splitting the data into 2 subsets: numerical data and categorical data. We first start by splitting the data into 2 subsets: numerical data and categorical data, that allow us to create a corpus that contains only categorical data, and then we convert to lowercase all the data and our label into numeric form. Before further preprocessing of the data, we have to always check if there are any missing values in datasets. If there is some missing values, then we can use techniques such as data imputation, but in our case, for the dataset, there were no missing values. In natural language processing, NLP, tokenization plays a significant role in dealing with text data. Therefore, in our study, we have used the word tokenization, 1-gram sequence or unigram, in order to have each categorical data as a single word. The back-of-word model builds a vocabulary from a corpus of documents and counts how many times the word appears in each document. Therefore, we have used the term frequency, inverse document frequency, TF-IDF, in order to discover how many times a categorical variable appears in our corpus. We have used the vector space models to discover relationships between categorical variables and visualize those relationships in the corpus. Here, we can see that variables that share common context in the corpus are located close to one another in the space. After tokenizing our data, we apply a vectorizer to the train and test set separately. Therefore, all the tokenized data can be learned from the vocabulary where tokens are terms and values are indices in the feature matrix. As a result, we have the TF-IDF weighted document terms matrix or the feature matrix, which is a sparse matrix. This process can also be called feature learning technique, where categorical data tokenized from the vocabulary are mapped toward vectors of real numbers. We have used different machine learning models such as logistic regression, multi-layer perceptron, random forest, gradient boosting, and deep learning, and we train and evaluate this model using the training and testing data encoded with a deep learned embedding technique. We evaluate the performance of different machine learning models by using the following metrics: accuracy, precision, recall, area under the RC curve, F1 score, and mean square error. The results presented in this table show that when encoding categorical data with target encoding, the gradient boosting outperforms the other models and gives higher accuracy along with the precision. Using binary encoding, we also built different machine learning models, and the results show that when compared to target encoding, binary encoding gives a lower accuracy and low precision as shown in the table. For the reason that 1-hot is the most used encoding technique for categorical data, we made a deep comparison between 1-hot encoding and our deep learned embedding technique. Our proposed technique, the deep learned embedding technique, gives higher accuracy than 1-hot encoding, and the precision is 0.83 higher than 0.79 for one-hot encoding as shown in the table. Here, considering the accuracy, as shown in the table, one-hot encoding surpasses our proposed technique. However, our proposed technique performs a higher F1 score of 89% than 71% of one-hot encoding in consideration of the LSTM model. The results that are shown in this table show again that using our proposed technique to encode categorical variables helped the machine learning model to have good accuracy and better F1 score than when using one-hot encoding. For instance, the LSTM outperformed 65% of accuracy compared to 61% of one-hot encoding. And further, the F1 score metric is 0.86, higher than 0.66 for one-hot encoding. Our proposed technique works well with artificial neural networks such as LSTM because it's based on word embedding. As shown in the figure, the deep learn has better accuracy than one-hot encoding. Another important point while dealing with categorical variable encoding is the number of features that can be generated after encoding. Besides the number of generated features after encoding, it's also essential to know the memory used by the data frame. Therefore, we have only applied the deep learned embedding technique on the categorical data, and after encoding, in the view of the back marketing datasets, the one-hot encoding generated 46 features and our technique generated 39 features. Here, note that after encoding, we have to concatenate all the data. That means we have to put together the categorical data encoded and the numerical data. The study aims to find a new way to encode categorical variables that can be nominal or ordinal data based on the word embedding. It is possible to convert a categorical variable into a numeric form, even if there is a semantic context or not between categorical data. The goal of this study was to find out the new encoding technique for categorical variable on a categorical dataset, such as the bank marketing dataset, .income dataset, and in-vehicle coupon dataset. The study shows that the deep learned embedding technique performs the best accuracy and precision compared to one-hot encoding. The deep learned embedding technique used less memory and generates fewer features than one-hot encoding.